In this lab experiment, you will be using fluorimetry to determine thermodynamic parameters of a rhodamine B cyclodextrin inclusion complex. First, you'll need to calibrate the fluorimeter. In order to do this, you'll need to make sure that the fluorimeter is turned on prior to logging into the computer. In order to log into the computer, you'll need a specific username and password that's specific to the fluorimeter itself. Therefore, you'll need to follow the instructions on the paper that's attached to the computer to get into the computer once the fluorimeter has been turned on. To calibrate the fluorimeter, you will need to use HPLC grade water, which is available over near the sink in the lab, in a quartz cuvette, being sure to fill the quartz cuvette at least 3/4 of the way full. Remove the top to the sample chamber and carefully place the quartz cuvette with the HPLC grade water into the sample holder, making sure it's completely down and secure with the top on. And then replace the top and make sure it's secure so that light from the lab does not enter the sample chamber. First, you'll want to click on the fluorescence software. Once the software is open, you'll want to go to the main experiment menu, which is this M in this top area, this top toolbar. Click on the experiment menu and click Spectra. First, we're interested in calibrating the excitation monochromator. So click Excitation, Next, and deactivate the emission by clicking the check mark so that it goes away, since we're just interested in the excitation spectrum. Click Run. You'll be prompted to enter a project name. Since this is just the calibration, click Cancel, and you'll see that the spectrum has appeared in a separate window. Within this separate window, double-click, and it'll bring up an interactive window. Expand this interactive window, and you're interested in where the peak maximum is with respect to the wavelength. In order to pinpoint this, you'll want the reader, which is this large crosshairs, and click on it and pinpoint as close as possible to where the peak maximum is. You'll notice that this is actually at our desired value, x equals 467, which is 467 nanometers. But let's say that it's at a different value, say 500, from where it's actually expected to be. At this point, we will have to manually correct the position of the monochromator. In order to do this, close out of this, and click Delete to delete the spectrum. Go back to the main experiment screen, hit Spectra again, hit Excitation again, click Next, and deactivate emission as before, except now, instead of hitting Run, we're going to hit RTC for real-time control. Click on Monos. You'll notice that you have position control here of the monochromator. In here, you'll want to enter the actual wavelength at which your peak appears, the errant wavelength. So in this case, we said in our theoretical situation that it's 500. At this point, click Calibrate Excitation, and you'll notice that it's at 500 in the current position, but your peak of interest, the expected peak location, needs to be where we want the calibration peak to be, which in this case is 467 nanometers. So in this box, type in 467 for 467 nanometers. And if we were going to change it, we would click OK. But in this case, the fluorimeter is actually already calibrated, so I'll just be clicking Cancel. You are now ready to calibrate the emission monochromator. Return as before to the main experiment menu, click Spectra again, and Emission. And as before, since we've already seen the spectrum and seen where the errant peak is, click Real-Time Control. Once you've clicked Real-Time Control, go to Monos as before. And instead of calibrating the excitation, we want to calibrate the emission. So click on the tab that says Emission 1. And again, pretending that our peak has been shifted by about 50 nanometers to 450, we would type in 450 nanometers, which is the errant position of the peak. And then click Calibrate Emission. And here we would enter the actual value of the peak, what it's supposed to be, which in our case is 397 nanometers for the Raman peak of water. And then we would click OK. Of course, our spectrometer is already calibrated, therefore I will not be clicking OK. I will be clicking Cancel to exit the screen. In this section of the lab, you'll be investigating the Beer-Lambert behavior of the rhodamine B dye. You'll want to make sure that you have at least 5 serial dilutions of the original stock solution you've created in accordance with the lab manual procedure. So in order to investigate this behavior, the first thing to do is obtain an absorption spectrum of the rhodamine dye in order to figure out what the best wavelength is to excite the rhodamine for the fluorescence spectrum. So the first thing to do is take one of your rhodamine solutions now in a plastic 4-sided cuvette and place it in the sample holder. Replace the lid securely as before. So then we go to the computer and click the main experiment menu again. But this time we're going to click on single point because we're only interested in a specific wavelength at which the rhodamine B fluoresces. Here you'll see an excitation and emission wavelength set up. So for excitation, you'll put in the appropriate wavelength from the lab manual. And then for emission, you'll also put in the appropriate wavelength from the lab manual. Once this is done, you can click Run. You'll be prompted to enter a project name. This time you'll want to actually enter one, and you'll want to name it something appropriate. For instance, fluorescence RB for rhodamine B, Beer-Lambert, and the date. And be sure to save it in local disk C, users, public, and public documents. Click Save, and click OK. You'll notice now that it just comes up with one single data point, which is what we were interested in. The easiest way to make sure that this data is all kept track of is to enter it directly into Excel as you go. So you can open an Excel spreadsheet and have one column for your concentration of rhodamine B and another column for the fluorescence intensity that corresponds. And you can simply copy and paste, after highlighting, the fluorescence intensity in counts per second directly into the Excel file and continue. Also, if you want to retrieve these data points later, it's easier if you click into sample and name it based on the concentration that you used. So let's say this is 0.5 molar for the sake of argument. Then you can just leave that there, click the X and click hide or simply minimize, and the data will be hidden but on the left of the screen and accessible later. Repeat this for all of the other samples for the Beer-Lambert study, and you will have enough concentrations and intensities to construct the Beer-Lambert plot, which is necessary for carrying on the later parts of the experiment. Before finishing, also be sure to utilize water, the deionized water, in a cuvette in order to take a blank, which you would then subtract manually from all the intensity values, since there is no blank feature within this particular software. This concludes the day one portion of the activity. Make sure that you've saved all your files from the computer, including the Excel file that contains all of your data points for the Beer-Lambert curve. On day two of the experiment, you will now be making measurements of the cyclodextrin rhodamine B inclusion complex. First, you'll need to dissolve the cyclodextrin in an aqueous solution of the rhodamine B, which you determined the best concentration of from the Beer-Lambert study on the first day of the experiment. In order to do this, you'll need to place the flask, the volumetric flask you make it in, into the sonicator for at least 20 minutes. And then make at least 6 to 10 dilutions of this stock cyclodextrin solution, diluting with the rhodamine B solution of the concentration you determined from the Beer-Lambert study. So instead of using the sand bath to keep the cuvettes at a constant temperature, we're going to use a less messy method and use a dry block heater for the cuvettes, a thermostat. And before actually putting the cuvettes in this, you want to make sure that you wipe all the cuvettes off with a Chem wipe, and then make sure that they're capped so that you minimize evaporation of any of the solvent in there. So there's both a timer and a temperature setting on here. And as you can see right now, the temperature is currently set to 30 degrees Celsius. This is the set temperature, and this is the actual temperature. Stop indicates that there's nothing going on with the timer itself, which you can set later if you want to allow the cuvettes to equilibrate at a new temperature for, say, a couple minutes or so. So if I want to change the temperature, say, to 35 degrees Celsius, I just go to Select and press Select until the temperature is reached. And then click Run/Stop. And now you'll see the actual temperature is starting to go up until it gets close to hitting, or eventually hits, the set temperature. Additionally, there's a timer that you can set, and once you've reached the actual temperature, you can go to Select, keep hitting Select until you get back to the timer. The second part is minutes, so say you want 2 minutes, and then you can click Run/Stop, and the timer down there shows the actual time that's accumulated or elapsed. And at this moment, it's 0 because there have been 0 minutes that have elapsed. But what you'll notice eventually is that the 0 will turn to a 1, and then eventually to a 2, and then when the 2 minutes is over, it'll beep. And this is mostly useful for if you want to allow the cuvettes to equilibrate at a new temperature for a certain amount of time. Usually no more than 2 minutes would be necessary for this. And then at that point, all these holders are going to be at this constant temperature, and you'll be ready to do measurements in the fluorimeter. Now the actual temperature matches the set temperature, so it's safe to say that these are actually at that temperature, but in order to allow them to equilibrate, you'll want to use the timer setting, and you can set this to, say, 10 minutes, and hit run/stop, and you'll be able to hear a beep at the very end when it hits the desired amount of time, which in this case is 10 minutes. Since temperature loss can be rather rapid, and this is a highly temperature-dependent experiment, have your lab partner utilize a stopwatch to time exactly how long it's going to take to get from the sand bath to the fluorimeter to make the measurements. You'll want to make sure it's as consistent as possible so that the data is good. The following is how to take the spectrum properly. Remove the lid to the sample compartment. Make sure that your lab partner is ready with the stopwatch, and start the stopwatch as soon as the cuvette is removed from the sand bath and being dipped into the water. So, ready? Go ahead. Use a Chem wipe to ensure that all water on the outside and sand is off. Place the cuvette into the sample holder, as seen before. Close, and take the spectrum. This again will be a single point spectrum in each of the cases, and you will be able to save these values individually, and it will help to directly place those values, copy and paste them into an Excel file so that you can keep track of them as you go along. Be particularly patient with this part of the experiment, as the temperature control is very important, and also being sure that you get all your data points so that your nonlinear fit later in the analysis will come out properly. So to end it, all you have to do is unplug this from the outlet and make sure at the very end that you remove all of the cuvettes from it, and then store this in an appropriate location.
When you're ready to collect your scan, go to M and then select single point, and then fill in the optimized wavelength for the excitation and emission values. And then make sure that the excitation slit width is 1 nanometer and the emission slit width is also 1 nanometer. When you've got these filled in, you want to click Run to collect your spectra. And then the counts per second box is the intensity, so you'll want to copy that and then paste the value into an Excel workbook so you can save your data. You'll want to repeat this process for every dilution and also at all the temperatures that are required.
Now that you are done with the lab, dispose of the cyclodextrin and rhodamine solutions in the specified waste container. Be sure to rinse thoroughly with the rhodamine dye because it does have a tendency to stick to the sides of the glassware. Methanol may help your efforts in this case. Be sure also to log out of the computer and turn the fluorimeter off on the side directly before leaving the lab.